Welcome to This Explainer. Okay, today we're diving right into the microscopic battleground inside modern ion thrusters. If you've ever found yourself wondering how spacecraft actually propel themselves through the literal void of deep space, you're in the right place. We're going to demystify the fascinating plasma physics and, honestly, the incredibly intricate engineering trade-offs that make electric space propulsion possible. To really wrap our heads around this, let's start with a beautiful analogy. Think of it like a steady wind pushing a sailboat. You're not getting that violent, fiery blast of a traditional chemical rocket. The initial acceleration is actually super modest. But because that gentle push is continuous, it eventually leads to massive velocity changes over time out there in the vacuum of space. It's totally a tortoise and the hare situation. But when in that race, well, that requires an absolute mastery of atomic physics. So here's our roadmap for today. We'll look at the electric space engine, the anatomy of ion generation, the energetic cost of making those ions, how primaries boost efficiency, magnetic traps and geometry, and finally, balancing power and fuel. All right, Section 1, the electric space engine and harnessing the power of plasma. At the heart of every ion thruster is plasma. It's basically a gas made up of positive ions and negative electrons. And what's really cool about this state of matter is that while the whole gas has no overall electric charge, the individual charged particles inside it are highly sensitive to electric and magnetic fields. Usually, we use a heavy, inert gas for this, like xenon. The whole thruster works by creating and manipulating this xenon plasma, physically turning electrical energy into a propulsive force. Moving on to Section 2, the anatomy of ion generation, breaking down the actual components. If you look at a classic DC discharge ion thruster, you'll see it boils down to three critical pieces working in total harmony: a plasma generator, an ion accelerator, and an electron neutralizer. Basically, you've got a hollow cathode spitting electrons into a magnetic confinement chamber, while these heavy-duty accelerator grids sit right at the exhaust plane, ready to launch the fuel. The journey of the fuel through all this is totally sequential. Step 1, we pump neutral xenon gas into the ionization chamber, where it gets bombarded by electrons to create our ionized fuel. Step 2, we grab those newly positive ions and accelerate them through highly electrified grids, blasting them out at like 20 to 40 kilometers per second. That's our thrust. But step 3 is an absolute deal breaker if you skip it: beam neutralization. A separate neutralizer has to inject negative electrons right into that exhaust beam. If we didn't do that, our spacecraft would quickly build up a massive negative charge, magnetically yank that positive fuel right back to the ship, and literally cancel out all our thrust. Crazy, right? Okay, Section 3, the cost of making ions, or as I like to call it, the microscopic battle for efficiency. Inside that chamber, there's this relentless, invisible tug-of-war happening. On one side, you have ionization. This is what we want. An electron smashes into a xenon atom, knocks a valence electron loose, and boom, we have the positively charged ion we need for thrust. But on the other side is excitation. This happens when an electron hits the xenon atom but just kind of bumps it. It doesn't have enough energy to fully dislodge an electron. Instead, it just temporarily excites the atom, which almost immediately drops back to normal and dumps that energy as heat straight into the chamber walls. That is 100% wasted energy. The whole game here is managing the electron temperature, which we measure in electron volts. Physical models of xenon gas show us exactly how excitation and ionization energy losses compare at different temperatures. And here is the kicker. If your electron temperature dips below about 8 or 9 electron volts, that wasteful excitation rate actually outpaces the useful ionization rate. That represents a massive hurdle. It means at lower temperatures, a huge chunk of your spacecraft's precious electrical power is just radiating away as useless heat to the walls, rather than actually making the thrust-generating ions you need. Which brings us to Section 4, primaries. The efficiency boost using non-Maxwellian electron distributions. The physics models perfectly highlight the solution. Primary electrons have an astronomically high ionization rate. Because they form this high-energy, non-Maxwellian distribution, they pack way more of a punch than the baseline plasma. They are literally so powerful that having just a tiny percentage of these primaries zipping around can completely dominate the ionization process, effectively rescuing the whole thruster from those nasty energy losses we just talked about. But you definitely have to corral them carefully. By tweaking the geometry, like giving the thruster a larger internal volume, or by bumping up the internal gas density, engineers can greatly maximize the odds of a high-value primary electron smashing into a xenon atom before it hopelessly crashes into the anode wall. Seriously, bypassing that wall loss and forcing a collision is the absolute key to maximizing your discharge efficiency and generating that critical plasma. Section 5, Magnetic Traps in Geometry. Corralling the plasma. So how do we keep those super valuable electrons off the walls? Engineers build these invisible magnetic boundaries using multipole ring cusp magnets. These magnetic field lines literally act as a fence to corral the plasma. Since electrons are pushed around by magnetic fields, these traps dramatically stretch out the flight path of our energetic primary electrons. Instead of just flying in a straight line into a wall, they ricochet around the chamber, getting way more chances to strike and ionize our fuel. But, it's engineering, so there's always a catch. From a design perspective, the physical number of these magnetic rings dictates your performance, creating the ultimate engineering compromise. If you go with a 4-ring design, you massively lower the area where electrons can escape, which gives you phenomenal ionization efficiency, but you risk the electrical stability of the whole plasma potential. Now, if you upgrade to a 6-ring design, you increase the surface area, which brilliantly stabilizes the discharge, but you inherently sacrifice some of that hard-won fuel efficiency because more electrons leak out. It is a really delicate balancing act. Finally, Section 6, Balancing Power and Fuel, the ultimate real-world compromise. Zooming all the way out from the plasma chamber to the mission itself, we hit the ultimate real-world trade-off. On the one hand, ion thrusters give us incredibly high specific impulse, meaning they are ridiculously fuel efficient. By shooting xenon ions out at staggering speeds, we can pull off deep space missions that chemical rockets simply couldn't carry enough fuel for. But on the flip side, maintaining those complex magnetic fields, powering the ionization chambers, and juicing the accelerator grids demands massive amounts of electrical power, usually from huge solar panels or nuclear sources. And all of that power is needed just to generate a relatively low immediate thrust. Which leaves us with a pretty fascinating question to ponder. As humanity sets its sights further and deeper into the cosmos, how will our ambitions for deep space exploration adapt when our need for faster transit times starts to heavily outweigh the electrical power constraints of our spacecraft? Will we scale these exact thrusters up, or are we going to have to find entirely new ways to generate that crucial plasma? Thank you so much for joining me on this explainer. I really hope this helped illuminate the incredible microscopic ballets happening right now on probes out in the deep dark of space. Keep learning, and I'll catch you next time.